So let's go right into our session, which is called Camera Technology. So I would like to give the floor for the first presentation to Matthias Sonder from Teledyne DALSA. And the topic of the presentation is clarity at high speed. Matthias.
Thank you. Are we German, English? I guess I didn't even pay attention. Okay, good morning everybody. Thank you very much for joining us here. Matthias Sonder, as Patrick introduced me. Sorry for the delay. Why is the slide not coming up?
Oh, we have a technical problem.
Yeah, we've been suffering this morning from technology. So.
No, I think you have to look here.
Yeah, I'm looking here, but nobody can see anything.
Da ist auf der Screen keine Präsentation. Machen Sie das? Yeah,
you guys are lucky I'm the first one.
It's solved. Let's go on. Thank you.
Okay, great. Thank you very much. So I would like to talk a little bit about, Teledyne has grown quite a bit over the last few years. So this is news to maybe some of you, but I've tried to capture the breadth of what we do now between Teledyne DALSA, Teledyne E2V, FLIR, all these different groups that are now joined the family. I'll start with some industry trends that we're seeing at a high level, and then the consideration that drives for us as designers, as engineers, and the technologies we deploy, and hopefully we'll have some time for questions afterwards. So, short and sweet, the industry trends. In the past, all of this was about higher speed, higher resolution. Technically speaking, that's still the same today, but the motivation behind that is a little different. So today, we're being asked for higher speed and higher resolution, but with the purpose of more information. Like, you're really asking us for more data, more clarity on your objects, on your detection. You've gone from single field to multiple fields, so multiple aspects of the object that you're capturing. You don't want to do this anymore in multiple passes. You want to do one pass and get all your information. We all know color, monochrome color has gone, is there to stay, but the trend is going to more color, multispectral, hyperspectral, and 3D is also quite visible on the show here today. The whole motivation behind this really is a deeper understanding of what you're looking at. Right? We're looking at, we used to look for just object geometry. Today we want to understand what is the object made of. We want to know the material properties. We want to not just find objects, we want to classify them. We want to know polarization, spectral properties of the objects, all to interpret better what we're actually seeing. Of course, that also requires that we be smarter. We need to understand more of these objects. We need to do more processing. Everybody who has a desk probably has seen machine learning and AI come across it nowadays. This is in everybody's focus. And ultimately, every customer always asks for lower cost. Now, for Teledyne, this means lower system cost. So we help you make more efficient systems. We don't make cheap products, we make more efficient, lower cost systems with you. Now that drives consideration on our side. What do we need to think about to help you with your mission? We are looking at the dimensions. 1D, 2D, 3D is now coming up, and we'll talk about a couple of the products there. We are, of course, looking across the spectrum. Depending on what you need to see, you are looking at X-ray, you're looking at UV, you're looking all the way to long-wave infrared, maybe even terahertz imaging, depending on what you're trying to detect. And ultimately, you also need to look at different technologies. So you need to look at polarization, at spectral separation, and the two new ones here that I want to talk a little bit more about today is what we've introduced in the last couple of years in the linear HS. It's the multi-field approach, and I labeled this here as a smart approach because there's algorithms running in the system. It's basically the super resolution concept. So I'll talk about these a little bit more. So on the spatial technology side, so I'm using that term a little liberal, but the idea is you get different aspects of your object, right? So in a line scan sensor, this tends to be easy to do because the object passes across the image sensor, and as it passes different lines, you can get additional samples of information. So on the left side here, you see the concept of high dynamic range with with one line, or in this case, 3 lines with very high sensitivity and 1 line with high SNR, and you can then combine that information. The multispectral is by now a well-established concept on the top right. So the multi-field and the super resolution are sort of the technologies that exploit this concept of multi-information in a novel way. So I want to talk about those two a little bit more. The super resolution, we've just introduced that with the Linear HS 32K super resolution. So it's our highest end TDI line scan camera at the moment. And it uses this concept to create from 16K 5-micron pixels a 32K array of basically 2.5 micron pixels. The benefit to you is that you get really high resolution and really high MTF, high detectability of small objects, sub-pixel objects, defects, and you get this all with the benefit of the large pixel. So you have higher full well, you have lower noise, you can use the 5-micron optics you had before, you can use your 5-micron transport system, so you don't need to upgrade your system. You swap out the camera, and you get this high performance at a fairly attractive cost. I mean, these are high-end devices, but relatively speaking, you can use the optics that you have, and you get the higher bandwidth of the actual lower transfer rate. So this is a very attractive concept. Of course, you have every right to ask, does it work? Ultimately, of course, it depends on the application, but the customers that have been trying these are quite happy with it. You can see, I'm not sure how well it looks, but you can, on the left bottom, you see the low resolution image. That is one of the images that comes out of the camera. And then you see the high resolution image after we've done the super resolution reconstruction and applied the algorithm. In the graph, you see basically a factor that can be tuned in the algorithm is basically the MTF as a function of how much detail you allow the algorithm to restore from the information. Now, one thing I forgot to point out, I should explain this because it's quite important. This is not your 8K TV that upscales the video information, right? This is not a mathematical or even an AI-based upscaling. What this is a physical representation of the sensor. So you have a pixel, and the pixel naturally has some non-sensitive or less sensitive areas. And what we do here is we make sure that any sub-pixel defect is guaranteed to be captured in the image. So we have these two images, and we make sure that we capture sub-pixel defects and then reconstruct those defects back into the high-resolution image, depending on where they show up and what the contrast is. So it's a physics-based approach to super resolution. There's actual information going into the algorithm. So it's a very important distinction from upscaling. And that's why we're paying attention to calling this super resolution. Okay, so I'll be open for questions for this. Of course, next topic is the multi-field. Uses the same principle, multi-lines on a sensor. This can also be done with high-speed image sensors. If you have 3 different light sources, you can look at it with an area sensor and flash those light sources. Those things are possible. Here you can get the 3 light sources in this example with a single scan. Oops. And the way we're doing this is we have these specialized color filters on the sensor, and you can see the spectra up in the right. So we have really high extinction coefficients between the out-of-band colors. So you get a very high contrast between the blue and the red and the green, and you can use that to shine different light sources. In this particular example, I'm showing the different angles, so bright field, dark field, and backlight. And you can see the images there. There's virtually no crosstalk from one light source to the other. So you really have 3 independent channels that you can use to capture different information from the object at the same time. So I didn't do a very good job of making the link to the 2D sensors here because the animation doesn't work, but you can do multi-information capture very well with high-speed 2D sensors. Now we as Teledyne, we tend to work in a high-speed environment, so everything is about how fast can I do this. And with the line scan, we're doing it because you have the multiple informations in one scan. In an area sensor, you have no other way than providing frame rate, right? So you have to capture images really quickly, and then you can use that to create multiple pieces of information at the same time. And we have just launched the Falcon 4 11M with our colleagues from E2V. They've made the sensor for us. This is an 11M sensor capable of 600 frames per second. In an 8K resolution, in a 4K resolution, it does 730 frames per second. And up there is a video, which I cannot play, but you're seeing popcorn popping in a frying pan. So you can literally see how it jumps out of the kernel. It's pretty impressive. It's a very, very fast sensor for machine vision. Okay, then I would like to jump a little bit into the 3D. We also do a lot of 3D work. On the passive side, the stereo, well, you can do this with our sensors today, of course. This will be very interesting once we go into embedded systems and you can use those two images and create the data right away. At the time being, we have the active components. We have time-of-flight sensors. Again, the colleagues from E2V. If you come to our booth, please take a look. There will be a presentation this afternoon on this as well. The laser triangulation is our Z-Track family. I have a bit more information on this. We're now on the second family, the second generation there. And for structured light interferometry, we're supporting with different devices, applications like OCT or white light interferometry. This one is the example I wanted to show about the time of flight. I'll skip over this because my colleague will be talking about this later. Plus the videos don't play anyway, so come back this afternoon, please. Here's the Z-Track. This is the laser profiler from Teledyne DALSA. We're now on the second generation, 2K profiles, 2K resolution, up to 45,000 profiles per second, so it's a very fast application. But what I'm really excited about this device is the capability to combine multiple Z-Tracks into a common solution. So you can have a 360-degree view, you can avoid occlusions, and you can integrate this with our at-the-edge processing technology to get a much easier integration into the software that we supply. So that's a big step forward for ease of use. Okay, then quickly, I mean, this is nothing new. I just wanted to bring it up here for continuity. The different spectra are, of course, interesting for different reasons, right? X-ray, you can see through objects, so that's a technology we need to consider. And the visible, you can, for example, you basically exploit the different wavelengths to see different depths of your object. And if you're going beyond the NIR, we're talking about shortwave infrared. So here we're actually interacting, the photons are actually interacting with the chemistry of your object, with the molecules in the object. And you can see, you can measure moisture, you can see fat versus moisture contrast, you can probe chemical properties of your environment. And of course this helps detecting defects or detecting foreign objects in what you see here in food samples. And then the other interesting piece there is the seeing through silicon. That's a very interesting application for wafer alignment, for example, for defects in wafers. So that's where we supply the linear sphere at this point. And then at the far end, at the moment, is the long wave infrared. With the colleagues from FLIR, we are also, of course, expanding on this product line. But there's kind of two approaches here that you take. One is the visualization of heat. So in safety applications, in this case here on the amboss, of course you would like to know which of these sticks is hot. And with the camera you can see this, like if you're managing motor control or bearings that need to be checked, you can see, you can in real time watch if they're getting hot. On the right side you see the radiometric measurements, so you can measure temperature very, very accurately. And you've probably seen or heard about this for these fever cameras. Now in COVID days, you can have a camera, in our booth there's a sample, and it watches people in the room and measures their temperature. And then the last section here about technology is sort of all the things that didn't fit otherwise. There is one thing that is important, more and more important, is the data transfer, right? So our high-end cameras nowadays are all in the sort of 6 to 7 gigabytes per second. So we're all in that blue band already. And that's where PC, even the generation 3 PCI bandwidths can't keep up anymore. So you simply can't get that data into the host. The linear HS32K super resolution that I just talked about actually produces something like 12 gigabytes. So you actually need 2 frame grabbers to make this work, right? So the days of, okay, we can simply plug this into the computer are long gone, and we need solutions for that. We've all gone to higher and higher speeds, but I'm really wondering, this arch on the right side there, is there not a smarter way of handling all this data? Can we not do some at the edge data reduction in some form? And that's obviously something we're thinking about, and we'd like to think with you about that. Before I go more into those details, I wanted to mention one piece of the cost reduction. I didn't actually point this out too much in the beginning, but we obviously are trying to help you, our customers, with cost reduction. So here's a way, if you don't need the absolute highest end performance of your system, we are now offering the option of combining multiple cameras into a single frame grabber. So you can, if you are in a bandwidth regime where you need a frame grabber, at least you can use one frame grabber for multi-cameras. Right? If you're using a linear HS, yes, you need a frame grabber, there's nothing we can do about it. But here you can reduce the cost by having a single frame grabber. We have this in the fiber module as is shown there. We also have a CXP option. That's something that helps. So then I wanted to just finish off with the smart part. There's, if you imagine this high data stream that's coming from the sensor, and you have to read this all out. Well, what do? When you have an application, like on the left side, for example, these pills, right? You really only care about the yellow pill. All the other stuff you don't care about. So can we help you find a yellow pill and only send you the information of that yellow pill? Either the address or a location or a small picture compared to a large picture. Those are effective forms of data reduction that help you in the application, and we don't have to transmit that whole image stream. Identification for barcodes would be the same story. If we just sent you the code and you never actually need to see an image, your problem is also much reduced. And those are things we can do already, and we are of course working on expanding the bandwidth for these. I've put in the astrocyte workflow there. That's our tool to help you train a neural network that can then run in the camera. And the last example I have here is where that tool actually created an application that runs in the black box camera there, the LS245. This is specific for traffic. If you don't like the form factor, come talk to us at the booth. There's things we can discuss. But ultimately, that camera is capable of watching traffic on the street, the cars passing by, and it will track the car and the number plate until the number plate is in the right parameters and can be captured. And once you capture the number plate, the camera will cut out the car, it will cut out the number plate, and it will read the number plate and decode it and only send you those cutout images and the number plate. So ultimately what the user gets is, instead of 20 frames of useless image, they get a reduced frame of just the driver and the number plate. Exactly what they want. So that whole concept of data reduction is well applied in this example. And yeah, that's it for today. So thank you very much. I even have some spare time. So I guess we have questions afterwards, probably, right?
Well, we have time for maybe one question or so. I look at the chat. There are no questions in the chat.
Okay.
So thank you very much, Matthias.
Yeah.
Give him a hand.
Thank you.
Very informative.